Hi, good morning, and today is the 15th of April 2021, and every week at 8 a.m. On Thursday, London time, we like to do these live webinars, so I'm just going to sort of jump into it rather quickly today. So we've got quite a full list of questions today, so let me just go into it. So every week we do this webinar, and in the the webinar is really a reflection of the ZP Developer Zone. So in the ZP Developer Zone, we have these webinars every week. We have the Developer Zone itself, which is a website, and I'm going to say today that we're putting some free products up on the Developer Zone for our Developer Zone members. We have our Academy, we have our collaborations. I mean, we're starting a new collaboration pretty soon with a group in Sweden, which sounds quite interesting. We also post jobs also on one of the forums in the Developer Zone. We have a questions and answers, and I think it's very cyclic that we ask questions and you ask questions and we give answers, and also the Developer Zone members give answers as well. So I just want to say that the live streaming that we do every week is essentially driven by the forum. So in the forum, people ask questions, and then we kind of collate all those questions and essentially put them into this webinar that we do once a week. So this week we've had really quite a few questions. So one of them was was about Djuli and EIS. So Djuli is an online database for the storage of electrochemical data and the manipulation of electrochemical data, and you can share your electrochemical data as well. And we've talked that there's an EIS function coming, so I'm going to do a demonstration on Djuli today. There's also been a question coming from Phil Wong regarding hi guys, I can see Hasim and Yanni online. We had a question from Phil Wong asking about if he puts a Nathan coating on an electrode, it really should make an impact on the EIS spectrum, and the answer is yes, it should. We'll try and do some simulation around that today to try and sort of answer that. We've had from Census in Uppsala, the guys are asking about common mistakes when developing, probably when developing biosensors, and be mindful of cyclovoltammetry. And some changes when you're making biosensors, and also a comparison between cyclovoltammetry and electrochemical impedance spectroscopy. So I'll sort of say it in this presentation today that I used to be quite a fan. A fan of cyclovoltammetry when it came to doing biosensors. When the biosensors I'm thinking about at the moment, as I say that statement, are binding assays where you've got this sort of antibody and the virus of interest comes in. I used to be quite keen on cyclovoltammetry, and then through the work at ZP I became more interested in differential pulse voltammetry and then square wave voltammetry. But these days actually I'm quite a fan on EIS spectroscopy, electrochemical impedance spectroscopy rather. So I've actually changed my mind quite a bit. So we're going to try and go through this and answer a lot of these questions this week. So the next slide is just to really say, right, we did have an inquiry about Djuli, and I said that EIS was coming to Djuli, this impedance spectroscopy. So let me just change to the browser and just say a good place to start with Djuli is go to the knowledge base part of our website. There you can either get you can log into Djuli, or you can go to the Learning Center. It's probably worth saying on the Learning Center button we have chronopotentiometry data and chronoamperometry data. So I know the question was about EIS, and that EIS function is still coming, but I wanted to do a bit more of a demonstration on Djuli today using amperometry. Now we have done a potentiometry demo in these webinars. It wasn't last week, it was the week before. So we have, but essentially there is data that you can download on our website. So the potentiometry data, there's four sets of data there, and for the amperometry data there's 3 sets of data here. So you can download this data and you can essentially kind of start playing with Djuli using our data, which means you can kind of get going a little bit quicker. So what I'll do first is I'll log into Djuli, which is what I'm doing here. So Djuli is free to use. There's a training module that goes with it, and for developer zones, developer zone members, that training module is free. And whoops-a-daisy. So what I'll do is this. I'm opening up a report, and I'm going to look at chronoamperometry data. And as I say, the chronoamperometry data is on our website. You can download it. So what I'm going to do is I'm going to go into edit mode. I'm going to go to tools. I'm going to upload the data so I can see that. So this data, I downloaded it earlier on off the website, and now I'm going to upload the data. So essentially the data is getting uploaded to our website. So I'll just show you where, up to Djuli. I'll just show you where that is again. So if you go to knowledge base and you go to Djuli, I know it's a bit convoluted, and the learning center, you can find some test data here. So I'm using this chronoamperometry data here, so you can download that. So if I go back to Djuli, I've uploaded the data now. So I've now essentially, I've been in the lab, I will have gathered my, in this example, chronoamperometry data, and as I say, we've actually done chronopotentiometry data in the past. So next thing I'm going to do is I'm going to go, this is a continuous study. What we mean by that is we've been watching a signal as a function of time. So it's amperometry data, AC, and then I'm going to just go raw data, and I'll close it. Alright, so this is what it's now done. It's essentially, I've uploaded the data, it's now extracted the data, and now it's displaying me the data. So this is a kind of classic, for us, glucose experiment where we've got 0 millimolar of glucose, and then at a certain time point we've added in some glucose and the signal's gone up. So it's a classic chronoamperometry experiment. Just saying hi to everyone. It's a classic chronoamperometry experiment, and so Djuli allows me to upload that data, and essentially now I could share it from here with colleagues. What I'm going to do next though is actually analyze the data. So if I go back into tools, I'm going to do fit step. I'll do statistical analysis. I'll close that, and what it wants me to do now, it wants me to say, tell me at what, it says essentially what I need to do is I need to tell it some properties of the data. So if I essentially if I tell it here at this time point at 400 seconds, actually I'm going to do it at 750 seconds, and I'm going to tell it the concentration was 0. I'll make that window a little bit narrower like that. That's, but it says it's done. It's not. I need to add a another data point, which is at 2 seconds. I'll put in 1500 seconds. I'm putting 10. I just want to move that data point a little bit because you can see that I said 1500 seconds, but that's actually there. I need to get it on this plateau. So let me go into 1750. Let me put 1750 seconds in. So now what it's done, if I just go back into here, it's just, I've told the data that at 750 seconds the concentration was 0, so around about here it's 0, and then I've told you at 1750 seconds, which is about here, the concentration was 10. So now it's essentially got 2 points which can do its calibration off, and it's done it's basically done a sort of a linear fit, It's not amazing because you know, actually there's quite a bit of variation in that data. You know, that those two sensors are similar, but that one's not so good. And it's done the standard deviation, so you can kind of see that, you know, we got a 30% standard deviation in that data. But it's pretty powerful that essentially you can download our data to play with this, and then you can upload the data to this. You can essentially bring 3 sets of data together in one graph, which is what we've done. And then you can say, right, well, my concentration was this, and my concentration was this, and then it will do all the statistical analysis for you. It will tell you your slope, your intercept, your standard deviation. It'll tell you your limit of detection. It'll tell you your R² value, and it'll give you a whole, say, bunch of statistics. Essentially, you can see that at 0 millimolar, we've actually got very consistent data. It's just when we went to the 10 millimolar, you can see from this box graph that we essentially had an outlier, and you can see that essentially in the raw data there. So I went rather quickly, and I'm going to just do a summary. So Djuli is free. You can register for it. We've got, at the moment, it's been designed for potentiometry quite well, and there's some potentiometric data you can download and play with. There's some amperometry data now that you can download and play with, and we are going to get towards EIS. So I wanted to bring that up because it was one of the questions, and I did say that we are bringing EIS to this, but today it's good for amperometry and potentiometry, and you can register for account for free. There's a training course on the Academy. If you need to access that training course for free, which you can, just drop me a line and I'll send you a 100% discount code. Right, I went quickly, see, so there's a lot to cover today. So that was, I wanted to cover Djuli a little bit today, give you a bit more on that. Now, one of the questions that came from Phil Wong was actually about Nathian. So it's worth knowing that the piece of software I'm going to use is available on the website. Now, I think if I read Phil's question correctly, essentially I think he has an electrode and he puts a Nathian barrier over the top of it, essentially a polymer, and I on a full polymer, and he says, you know, my EIS, my electrochemical impedance, doesn't change much. And that really just tells you that I don't think the Nathian is adhering correctly to the electrode or covering it correctly. So I'm going to do a simulation. So as I say, this software is free to download off the link. So I'm just going to sort of demonstrate to you what I would expect. So if you go edit, whoops a daisy, model, clear model, library of models, I'm going to put in a Randall circuit. If you're not sure what a Randall circuit is, Google it. We have talked about it in one of our EIS webinars, but it's sort of fairly, you know, if you're doing electrochemistry and electrochemical biosensors, you'll hear about the Randall circuit an awful lot. So just say hi to one of the guys on who's watching. Right, I'm going to so I've brought up what's called the Randall circuit, but I just need to change this element from what's called a constant phase element to a capacitor, just to make it simpler. So Phil's question is, if I take an electrode and I put a Nathian barrier over the top of it, you know, should my, you know, EIS spectrum change? And the quick answer is yes, it really should. So what I've done is I've said, look, there's a free bit of software on our website, get hold of it, import a Randall model. I'm just going to leave the default values here and I'll simulate it. So you'll get a Nyquist plot that looks like this. Now, for the bare electrode, you might have some values that are sort of around this kind of region where the circumference of this circle, you know, you can see the way it crosses the circle at about 2000 ohms, and that's because R1 is 1000 ohms and R2 is 2000 ohms. Now, if Phil puts a polymer on top of this bare electrode, I would expect the capacitance to increase. So what I'll do is I'm going to take out a couple of these zeros. So I just want you to watch the circle. I haven't hit simulate yet. But look, that's at 500 and that's So the peak height here is about 500, and that's here is about 2000. I took out a couple of zeros, I'll simulate it. There's hardly any change. So it tells you really that a big change in capacitance doesn't necessarily lead to a big change in the Nyquist plot, which is actually really interesting because it's going to be at odds with something I'm going to talk about in a bit. But what I really expect to happen is if Phil puts a Nafion over the top of his electrode, I'm really expecting it to increase the R2 here, sometimes called the RCT, the charge transfer resistance. So I've just increased that by 2 orders of magnitude. I'll simulate, and then it should distort quite considerably. So the quick answer to Phil is this. If you take a bare electrode and do an EIS spectrum on it, you should expect a certain kind of Nyquist plot, let's say. But if you put essentially an insulator on top of it, you shouldn't change the capacitance and the resistance quite dramatically. And the EIS spectrum should reflect that. If it doesn't, the membrane's not on there. I don't know where it is. It's either delaminated. I'm not going to say it's dissolved because it's Nafion, but it's not on there, or it's extremely thin, let's say. So that was one of the questions this week, and I think the take home from this is if you want to kind of practice with EIS spectrums, and I think this get hold of this software is not a bad option. So like I say, I have to go quick because we've got a lot to get through today. So we've had a lot of questions really about biosensing again, and doing essentially virus detection. So if you're going to do a virus detector, I would simply suggest looking at papers such as this one, which is in IEEE. So essentially in this one, it's quite a simple sensor, and simple is always a good start in life. So what they've done is they've taken a carbon electrode. They've done cyclovoltammetry on it. So when we're forming biosensors, we often follow each step with a bit of not with electrochemistry. We like to follow the steps by cyclovoltammetry so that we can see that we're actually modifying the surface every time. Otherwise, you do several steps, you get to the end, and it didn't work. But of course, if you're doing cyclovoltammetry after each modification of the electrode, you can at least follow that, something is changing every time. So you take the carbon electrode, you do a cyclovoltammogram on it. You might bring your linker molecule here, which is a pyrene, and you will functionalize the surface so that it's so you can bind macromolecules to it, and you'll follow that by cyclovoltammetry. It was quite unusual in this case, in this particular paper, because modifying the surface ended up increasing the peak height, which was a little bit unusual, but this does happen, and so we went with it, and this overall the sensor did work. But the next part then is to bring the antibody in, so that now that you've turned the electrode into a functionalized electrode, you bring a reporting molecule in. We often use 5 millimolar ferricyanide. Oh, sorry, that's a blocking molecule in this case, which is often in this paper they might have used chitosan. Chitosan's fine, BSA is pretty good as well. At which point that really modified the surface by cyclovoltammetry, which is a little bit like the conversation we were just having at Phil's question. If you're going to put proteins or polymers on electrode surfaces, they really will modify them. And so if you can't see the modification by EIS, you haven't succeeded in immobilizing the material onto the electrodes. We do have a free course on this kind of work, which is on the Academy. So the previous slide was how to make the sensor. Now I want to talk about testing the sensor. So you've modified your electrode. You test it with 5 millimolar ferricyanide, for example. You get in this case it's differential pulse voltammetry. We're not using cyclic voltammetry, but essentially, in order of merit, when you're doing biosensor testing, I suggest differential pulse voltammetry and differential pulse voltammetry and square wave voltammetry are slightly better than cyclic voltammetry. But I'll also make a comment on EIS in a bit as well. But we test with no antigen present or no virus present. We get a signal. You add into the antigen or the virus, you get a new signal. And you keep on adding in increasing amounts, and the signal should change accordingly. And this is the actual data from that particular paper, so it did actually work. Now I have changed my mind, and the reason I've changed my mind is we have been doing these kind of binding assays where we have an antibody bound to the surface, and we might bring in a bacteria or a virus or protein, and they bind, and that essentially blocks the surface. We've been using EIS quite a bit recently, and I've actually become much more persuaded to actually say that EIS is actually a really good way of looking at these kind of binding assays. So historically I was started off with cyclic voltammetry, you know, sort of 15 years ago square wave voltammetry and differential pulse voltammetry started appearing. EIS has been around for a while, but nowadays I'm actually suggesting EIS is better. I mean, what's really good about this is, I mean, there is an outlier there that's, you know, a little close, but these are all handmade sensors, and so to have this kind of fairly good separation, I mean, you know, 5 and 50, you know, that's a tenfold increase. I do respect that fact, but it's not bad for handmade sensors. So we sort of plot the data out and essentially say that the capacitance is the source of the signal in this case, which is kind of unusual. You know, that a lot of people actually say that the RCT, this value here, is often the source of the signal, but for us it's actually the capacitance. So I just kind of want to flag that up, that, you know, you have to kind of construct your equivalent circuit, and the best source of signal is not always what everyone says in the literature, which would have been R2 or the RCT. It's actually, for us, this capacitance. So let me talk about making biosensors in the lab. So this is some old slides, so I'm going to go quite quick. Slides that we've given in the past. I'm going to go quite quickly, but it is relevant because we do have a new group that have joined us from Sweden. They're very interested in making biosensors. So once upon a time, we had all these questions came through, and the guy said to us, you know, he had 2 points and a lot of questions, and the 2 points were, he really liked the ZP sensors because of they were giving really good results. Now, I think that's because we also support, you know, the sensors quite a lot, especially to these webinars, so that, you know, people have a good experience of these sensors. But he was struggling with reproducibility, and so really had a series of questions about, well, how do I get reproducibility? And so the next few slides will say, you have to put the antibodies on the working electrode, don't cover the counter and reference. That's a good lesson. We tend to drop coat the sensors, so we pipette down, we don't dip coat, so we drop coat. We control the rate of evaporation. If you don't control the rate of evaporation, you'll end up essentially having variable sensors. And also, I mean, when we're doing biosensor development, we're not testing one sensor at a time. We're testing, I mean, at this point we have at least 5 12-channel instruments in the building, along with all the single channel instruments. So, you know, we can't test one sensor at a time. It takes too long. You know, we're testing 12 at a time. Now, that's okay for a company like us. I get the point that, you know, it's an expensive investment, but that's essentially what we're having to do to do biosensor development. So just a couple of points. So we have a whole range of electrodes at Zimmer and Peacock. What makes them a little bit different is that we really do a lot of characterization called wafer mapping before we even ship them. So we're fairly certain of the quality before we ship them. I can see Shirley's online, and Shirley's one of our engineers, so she knows the kind of, you know, how well we try to do the work and the professionalism with which we try to do it. But we do check all our electrodes before they actually ship, which means that people making a biosensor on top of them having a good start in their development. His question was, how do you functionalize? So we don't functionalize by taking the sensor like this and just flooding it. We functionalize it by doing quite accurate pipetting of solutions along the electrode, and then we might just draw the pipette along and essentially paint using the tip of the pipette then to kind of cover that electrode. We actually use robots when we're really going to volume. It's not practical obviously in an academic setting, but essentially we hand pipetting when we're doing development, and then we'll take it to a robot later on. And going to a robot will allow you to get to the next level of reproducibility. The other part was, how do you control evaporation? I mean, here you can see how many electrodes we've made, and essentially we're controlling evaporation by controlling the vacuum above the electrode. So, so we're trying to get a reproducible evaporation of the solvents. If you don't do it in a reproducible way, then it will be a source of variation. And then in order to get the kind of numbers it takes to really make a biosensor, we're not testing 1 or 2 or 3 or 4. No, we're testing like 12 at a time. So we have a real workflow, where chemists are making up solutions, technicians are potentially pipetting down, and then somebody else actually might be testing. The data goes to the Djuli database, and then we're doing analysis. And there's at least 5 people involved, in that biosensor workflow. And lastly, we're doing it in a very controlled environment. I mean, these are clean rooms. The temperature and humidity is controlled. So the guys are all very gowned up, so that they don't actually. So Abro's asking, for the next webinar, is it possible if you explain how to use polysaccharides as a receptor immobilized onto electrodes? Yeah. Abro, if you can put the question onto the forum, then I can pull it off the forum, because we're using the forum now to gather questions. But in order to make a good biosensor, you need a controlled environment. If you haven't got a controlled environment, you can still do it. It's just, it will affect your reproducibility. I mean, and this is the kind of environment and controls that we take in order to make biosensors that are not contaminated in any way. And we are ISO 13485. I've got 3 minutes left. I'm going to go quickly. A little while ago, Hasim asked questions about microfluidics for biosensors. I would like you to potentially just Google capillary fill sensors on Zimmer and Peacock and just watch a video there. So you'll see a video where a sensor fills by what we call capillary action. Essentially a in vitro diagnostic. So many of you are actually developing in vitro diagnostics. You need a electrochemical sensor and you need microfluidics. So we just spent 28 minutes talking about electrochemical biosensors. We're going to spend the last 2 minutes talking about essentially in vitro diagnostics and how to rapidly prototype them. So Hasim asked this question ages ago, and I said, look, we're coming up with some STL files. STL files are files that you can print on a 3D printer. And so essentially we're giving you the tools to make microfluidics on top of the screen printed electrodes. So I showed this picture a while back, and it's worth saying now that we've actually made these things now. So this is our screen printed electrode, and we've bonded the 3D printed microfluidic chamber to the screen printed electrode using a pressure sensitive adhesive. So these files are called STL files. You can download them off the developer zone, and you can essentially print them. So what I might do, I'm going to come to my summary in a minute, but let me just go to my website very quickly. I can see the time is 8:29, so I'm going to try and be very quick. So I am going to be very quick, and I'm just going to go, developer zone. If you go to the developer zone, you'll essentially find that these files, now they say 125 euros there. It's just to stop non-members just coming in and taking them. But if you're a member, just contact me and I'll give you a 100% discount code and you can download them. So they're STL files. They allow you to essentially print out on a 3D printer these little chambers, and then all you need essentially then is, you've got the STL file, so you'll be able to print the chambers yourself. You just need screen printed electrodes. The hypervalue electrodes are really the ones I advise. You need these adhesives. These adhesives come in 3 types: rectangular, circular, and square. And that's because on the developer zone we have 3 types of chambers: square, circular, and rectangular. So you need to get the corresponding adhesive to go with that 3D printed part. So essentially, you have a screen printed electrode, you put an adhesive on top of it, and then on top of that you put the 3D printed chamber, and now you've made yourself a biosensor. Right, 8:30, 50 seconds. Summary. Okay. Thank you for all the questions. I might have to start doing 2 webinars a week because the questions are getting, a lot. Djuli, if you haven't registered, register. We've got chronopotentiometry data to play with, chronoamperometry data to play with, and EIS will come. We've talked a lot about making a biosensor today, and a biosensor is really not that useful unless you actually start dealing with the microfluidics as well. And we generally have put up free to developer zone members, free to you guys, STL files. You can download them, you can print the chambers, and then you just need the ZP screen printed electrode, adhesive on top of that, which you can also get from ZP, and then the 3D printed chamber, and you've now made yourself essentially a prototype in vitro diagnostic. Okay, well, thanks very much, April. If you post that question in the forum, I will pick it up from the forum and answer it. Appreciate it very much, everyone. And 8:31, 8:32, I better go. But thanks very much. Thanks, Haseem, and thanks, guys. Appreciate it very much.